So let's move into section 2.2 and start talking about limits. Now, just a little bit ago in my intro to this course, we talked about the rate of change of a function. Now, when you look at things between 2 points, 2 points that are kind of far away from each other, what you're getting is the average rate of change. And what I suggested we could do is make that point get closer and closer to another point, so that instead of getting the average rate of change, we get what's called the instantaneous rate of change. How is that function changing at an instant? Now, this process here of moving the slider actually has a little more of a formal math name. We're taking what's called the limit. Thank you. No, I appreciate knowing that. Am I back? All right. So as this function approaches, or as h approaches 0, these two values of the function approach the same thing, which is the limit. Now, let's take a look at what that limit's going to mean. So there's two ways you can approach a value, to the left and to the right of something. And let me kind of define for us what those are actually going to mean right here. So this is coming right out of one of your homework problems. It says, explain what is meant to say the limit as x approaches 6 from the negative side or from the left of f of x equals 7. So what that means is that as you get close along the x direction, so say here, as you get closer along the x-axis, what's happening to the y-coordinate? You want that y-coordinate to get closer and closer to 7. So as x approaches 6, the y-coordinate can approach 7. Now you can draw anything you want here, just as long as it ends up at a 7. So that's what's saying. It's like, okay, as you approach 6 from the left, the limit approaches 7. So the limit is actually the y coordinate of your function at that point. There's your 7 right there. Now how about the other side of things? Well, the other side of things says, well, now we're going to approach 6 from the positive side. So from the positive side, that's this direction. As you approach 6 from the positive side, then that limit is 4. So, okay, that limit's 4, like that. Now again, you're going to draw something in here, and basically what you want to draw is something that ends up at this point. So that the limit from the right is 4, and the limit from the left is 7. Now ideally, we'd like to see those things match. We'd like to see the limit from the left and the limit from the right match. If they do, then we can drop this plus and minus notation and just say, all right, well, the limit from the left and the limit from the right both go to the same thing. So let's say she draw something like that. So I'll put a little dot here. Let's call that point 2 and 4. Here and here. There we go. All right. So that's what we'd like to see. In order for you to be able to write this, both the limit from the left and the limit from the right have to be equal. Now, it doesn't exactly matter what's happening at the actual point. Notice I drew this hollow dot here. The function's actually not defined at this point. That's okay. So in this case, g of 2 is undefined. But what actually happens at this point in the limit can be different things. Now it's nice when they're the same because then you have a continuous function at that point, but this point doesn't actually have to exist in order for the limit to exist. So let's play with some more examples. All right. So if we open this up a little bit, we can move on to another example. So this is some function, we'll call it h of x. And let's start by taking a look at some of these limits here. The limit as x approaches -3 from the left of our function. Well, here's our -3. As we approach from the left, what this is asking us is, well, what y value are we getting close to? So as we come up here, what y value are we getting close to? 4. Thank you. So that would be 4 right there. So that's cool. Now they followed up, and I do this quite often in my exams. I follow up the limit on the left with the limit on the right. As x approaches -3 from the right, now what's going to happen? Well, you're approaching this way this time. But fortunately for us, in terms of the limit, you're still getting close to 4. So the limit from the left and the limit from the right are both going to the same thing. So what does that say about the limit overall then? What can I put in there? 4, yeah. The limit from the left and the limit from the right both equal 4. How about h of -3 though? What's going on with h of -3? What's the value there? It's undefined. You got a hole in the graph at that point, so that's okay. It doesn't affect the limit though, which is perhaps a little bit unsettling when you first see it, but that's okay. It doesn't have to be defined there in order for the limit to exist. Now, let's try that again at h of x is 0. We'll look at the limit from the left and the limit from the right near 0. So the limit from the left, this time we're approaching this way. What's the limit from the left of h of x at 0?
-1. Or undefined. 1.
We got a little debate here going on. -1, 1, or undefined? What do you think? 1? Yeah. So you're looking at the y coordinate here, and it's getting closer and closer to 1. In fact, the function is actually defined at that point. So, but the limit from the left is 1. So, nice. How about the limit from the right? So let's look at the limit from the right on this one. And this time we're coming from the right. So we're coming into here. Now, you're moving along the x-axis, but you want to pay attention to what's happening on the y-axis. So, let's see. Actually, you know what? It doesn't actually say to the right, does it? Yeah, it should. So let's put in a little plus there. Now it's the limit from the right. Now somebody think I had this just a minute ago. What's the limit as x approaches 0 from the right of h of x? What's that limit going to be? That's -1. Perfect. So what I typically follow that up with is this question. What's the limit as x approaches 0 of h of x? Yeah. Because the limit from the left and the limit from the right are different, this limit does not exist. If you want to put undefined, that's okay too. But I think you're typically going to see does not exist, DNE, right there. Now, unlike the last example, h of 0 is actually defined, right? What's h of 0 equal to? 1. Yeah, thank you. 1. All right. Let's try a couple more here. Now, this one is, again, kind of a good follow-up for me. It reflects the way I test some of these things. The first example we walk you through. I give you the limit from the left, limit from the right, and ask you what the limit is. After that, I say, okay, you're on your own here now. You got to figure out what's that limit. Now, in looking at that limit, you really have to realize that, okay, I've got to look at the limit as x approaches 2 from the left of h of x, and the limit as x approaches 2 from the right of h of x. And I got to make sure that those two things are equal. So let's look back at our graph. You're going to approach 2 from the left. and you're going to approach 2 from the right, even though you're approaching along the x-axis, you're really looking at what happens to the y-coordinate. So what we got? What's the limit as x approaches 2 from the left? 2. How about as x approaches 2 from the right?
2.
It's 2 again. They're both equal, so at that point, then you can say, okay, yeah, h of 2, or the limit as x approaches 2 is 2. Now h of 2 is once more undefined. It is what it is. Not defined, we're okay there. Let's look at 2 last ones here. And that's as x approaches 5 from the right and as x approaches 5 from the left. Now, I don't think you can really appreciate what they're trying to show here. Let me maybe give you a look at this. Maybe it's a little bit easier to see. But what they're trying to simulate here from the left is a graph is just going crazy, going up and up and down infinitely often as you approach from the left. So the limit from the left of h of x doesn't exist because it's just going up and down too quickly. So that one would be a D and E. But how about the limit from the right? Would you say, so the limit from the left does not exist. But how about the limit from the right? Is that getting close to some value? Yeah, it looks like it's getting close to this one, right? It's getting close to 3. So even though on one side it doesn't exist, we're looking okay on the other side. Nice. Nice. So what's the big thing with limits? What do you need to make sure when you're calculating a limit? What would I say here if I asked you the limit as x approaches 5 of h of x? What would you write? Does not exist. Excellent. Thank you. Does not exist. Because the limit from the left and the limit from the right aren't the same. In order for this limit to exist, both of these have to be the same. Yay. Okay, so I've stolen another one out of WebAssign, your homework. And if you want to follow the QR code, or if you're opening up this from the website, you should probably be able to just click on the link and get it that way. But where did it go? Where did it go? Maybe I need to open it up. No. All right. Just have to do it this way. Desmos. No, I don't. 2.2. Okay, so what they're giving you in this is a piecewise function. It's the cube root of x to the left of -1. It's x between -1 and 2. And it's x minus 1 squared to the right of 2. So it's a piecewise function. It looks like this. You can see you have, a little linear part. You have your cubic or your cube root part, and then your quadratic part. So, all right, nice. Now the question they ask you is determine the values for which the limit does not exist. Now for a limit some value of x where the limit from the left and the limit from the right might be different?
At x equals 2?
Yeah, at x equal 2. All right. Everywhere else, the graph is a continuous function. So its limits at all these points aren't going to exist. So rather than answering this by figuring out each point where the limit exists, we're just going to do it by figuring out where it doesn't exist. And where it doesn't exist is at x equal 2. So thank you, Nicole. So as you approach x equal 2 from the left, the limit is 2. What's going to be the limit as x approaches 2 from the right? It's getting close to what value? It gets close to 1. Now you can't actually, I guess you actually can get the 1 here. My bad, I didn't look over here. For a second I was thinking it was undefined there, but no, it is defined. That's probably a typo. Let me take a look back at the function. Yeah, it should just be a greater than. Just make that a greater than. There we go. So now it's not defined at 2. But regardless, the limit from the left and the limit from the right are going to be different. So the function is not defined at that point. Now, as far as the graph, as far as the answer to the problem is concerned here, WebAssign might want you to fill things in this way. So it's at x equal 2 is where the graph is not going to have a defined limit. So everywhere else, other than 2, the graph is going to be defined. So if you had to list it in intervals, it'd be negative infinity to 2, parentheses. Why a parenthesis? Yeah, because you're not including the 2. Union 2 to positive infinity. So basically, it's kind of a fancy interval notation way of saying everything but 2. That's what you're looking for there. All right. We okay with problem 12 there? How many of you have a graphing calculator with you today? All right, good. How many of you don't? If you don't, you can borrow one. You just got to trade me either keys or your phone, something you're not going to leave class without. Actually, I think you can also jump in on the QR code. Might be a different way to get this. But if you want to practice with the kind of technology that you're most likely going to be using moving forward, then come on up and borrow our calculator. Yeah. Yep. Yeah, that one's good. You good there? You too? It's all right. There you are. There you go. Wow. Okay. So ultimately, we're going to calculate limits in several ways. We're going to calculate them by looking at the graphs. We're going to calculate them by some algebra. And we're also going to calculate them numerically by looking at tables and seeing what happens to a bunch of points. So let's see here. Yeah, this one. This is the one we want to look at next. So it says we want to create a table of values to look at this function as h gets closer and closer to what number? You tell me what you think we're getting close to. They want you to evaluate things at h is plus or minus 0.5, plus or minus 0.1, 0.01, 0.01, 0.01. And I'm sorry I don't have enough acapella in me to do any higher, but what value are we getting close to with h? I'll give you a hint. It's right over here. 0. 0, yeah, perfect. You're getting close to 0. Now, I mean, you could be tempted to just put in a 0, right? But what would happen if you put in a 0? Yeah, it's going to be undefined. So I was going to invite us to do a little Gadonkadon experiment, which is what Einstein used to do. Thought experiment. And that thought experiment would be plugging in a 0. You'd end up with 2 to the 5th, which is 32. 32 minus 32 would put a 0 in the numerator. And then if you put a 0 in the denominator, well, you got 0 over 0 again. That's undefined. It's hard to know, well, what should I put here just by looking at this? You're going to have to do something. And we've got 3 choices. You've got some algebra we could do. We could look at it numerically. We could look at it graphically. So we're going to start by looking at it with some tables. So those of you who have not had me before, and those of you who have your own calculator, might want to follow along with this. We're going to first do the table setup, and it's important to get this right at the start. So if you hit the second button, then the window key, it takes you to something here called table setup. And what I want you to do is to mimic my table setup here to this point right here. The last 2. Independence should be set to ask. So if it wasn't, say it was set over to here, then what you do is you cursor over to ask and press the enter key. Hopefully dependent is set to auto. It doesn't matter what table start and delta table are. You should be okay there. But once you get those things set, let's enter our function. Now, with these settings here, keep them here for the rest of your life. Or the rest of this course, all right? Either one. But it's really convenient just to be able to do our own tables where we want and when we want. Well, let's go over to the y equals key. And wow, it looks like I got a lot of crazy stuff here. Let me clear that out. Looks like some pretty good stuff too. It's too bad. And you're going to need to be kind of clever in putting this in, depending on your calculator. So I'm going to put it in a way that'll work for everybody, and then I'll go back and circle around and figure out how to do this a little bit nicer for those of you who have a calculator that's up to date. You're going to put in 2 left parentheses. One's going to be for the entire numerator. The other one's going to be for that binomial 2 plus h. Except for convenience, we're going to do 2 plus x. 2 plus x raised to the 5th power. And if you're wondering, well, what keys am I hitting? The key history is right here below. So 2 plus x to the 5th. Then leave me with something here. You might want this one better. It's better. Yeah. And then what was it? Minus 32. Minus 32. Parenthesis. And then divided by x. So what we're doing is we're really just mimicking this part right here. I'm just putting in an x because it's just more convenient that way. So, all right, great. We've got our function entered. That's one way. For those of you who have an up-to-date operating system, you can do something else which makes it a little bit easier, which is kind of cool. But everyone should have this. Good? Good back there? All right. So if you got an up-to-date operating system, try this. Hit the alpha key, then the y equals key. And that first selection there allows you to do a numerator and denominator, just kind of like you would write it. So if you press enter, now it's not kind of a forward slash anymore. It's got this numerator and denominator. Now we can just do parenthesis 2 plus x raised to the 5th minus 32. Parenthesis. And then to get the denominator, you hit the down arrow key. So let me clear out some of this. Yes, clear out the history. And then I'm going to divide by x. So that's another way to do some of these things. They both got their pluses and minuses about them, etc. But one way or another, you should be able to enter this function. If you do, and when you do, let's go to the table. You're probably just as well off doing the first one. It's just I want to be very careful to point out that you need that extra set of parentheses around the numerator there. When you're all done, hit the second key, then the graph key. That'll take you to the table. If you've got some values there, just hit the delete key. Get rid of those. And now we can actually start doing what the problem is asking us, making a little table here, table of values. So they wanted us to plug in h is 0.5. Well, we're going to plug in x is 0.5, same thing. And there you go. And let's plug in 0.1. And then 0.01. So, okay. 0.001. And finally 0.0001. And notice that for your x's, it changes things over to scientific notation. So, okay. Now take a look at the y values. If you had to guess, what y value are you getting close to? What would that be? Yeah, it looks like it's getting close to 80. But this is the limit from the right, because we're coming to 80, but we're coming in from the right. What if we came in from the left? Say we had negative 0.0001 or negative 0.001, negative 0.01, and finally negative 0.1. So basically what we've got here is the limit from the left and the limit from the right. And they're both tending to what number? Both tending to get closer and closer to 80. Now, if you're not getting enough digits here, if you want to see more digits, if the thousands place isn't enough for you, you can take your cursor and go over to one of these Y columns and just move up and down. And along the bottom row of your calculator, you're going to see as many digits as you want or need. So, all right. So it looks like the limit is approaching 80. Now, the nice thing about working with limits is you can confirm this in more than one way. So it looks like that limit is 80. But let's take a look at the graph. So where's the graph? Let's see here. Let's shut this off. And get rid of those as well. How come that's not on? Oh. The reason we're not seeing it is because the graph is a lot taller than what I'm seeing now. So what I'm going to do is go to the tools, click that, and I'm going to move that up to, say, 100 on the y-axis. And there we go. So now we go. Now we're in better shape. Now we can look at the limit as x approaches 0 from the left or the right. So as you approach 0 from the left, we're getting closer and closer to 80. And as you approach 0 from the right, again, you're getting closer and closer to 80. Take a look at the y values on the graph. That point is showing you those y values. Now you can see those same things on your calculator. Let's just set up the window to do that. So let me exit out of here. I'll hit the clear button. And let's see. I got to set up a window to do that. -2 to 2 should be fine. And then on the y-axis, let's go from 0 to 100. Now, if I just left this as y scale equal 2, I'd have 50 tick marks up and down my y-axis. That's a little bit too many. Let's go for y scale of 20. Each tick mark on the y-axis is going to be 20. When I got that all set up, should be able to hit the graph key. And there you go. There's our graph. Nice. But what I wanted to do is I wanted to trace it. Now when I hit the trace key up here, it immediately puts things in the center of my graph, which I don't want just yet. So I'll just move a little bit to the left and then come back to the right with the trace key. And you can look at the y values. They're getting closer and closer to 70 or to 80. You just can't quite get there because at x equals 0, this function's undefined. That's okay. The limit still exists, and it's 80. All right. So we've looked at this one a couple different ways. We looked at it numerically, we looked at it graphically, and at some point I'm going to prove it to you algebraically as well to really kind of put a lid on this one. But are we okay with that one? Are you okay with the technology on that?
I got a different number, but I'm pretty sure I did something wrong.
Jeff, can you look and see if you entered the function correctly? All right. Anything else? Let's take a look down here at problem 16. I like problem 16 and problems like this. Let's see. So the first part of this is to draw a function so that the limit as x approaches 0 of f of x is 4. So let's put a little spot right here. That's where we're eventually going to get. This function has to have a limit of 4. Okay. What else are they telling us in this function? Well, the limit as x approaches 8 from the left is going to be 1. Okay. How about the limit as x approaches 8 from the right? That's going to be negative 3. So that's going to be down here. F of 0 is going to actually equal 6. Let's see. So f of 0 is going to be 6. Let's see. Oh, here it is. So I'm just going to put that spot right up here. F of 0 is 6. Let's maybe make that a hollow dot. And finally, f of 8 is actually going to equal negative 1. F of 8 is actually going to equal negative 1. So this would be an ideal test kind of question because you don't have to work with any complicated formulas. It's just a matter of, do you understand some things here? So let's see. Let's see if we can't draw something that matches all of this stuff. The first part of it is this, that the limit as x approaches 0 of f of x is 4. Now they're not talking about the limit from the left and the limit from the right. They're just saying the limit of this function as x approaches 0 is 4. So that means the limit from the left and the limit from the right have to be equal. So somehow or another you have to draw a function that as you come in from the left eventually settles down here at x equals 4. And as you come in from the right, same thing. Now it doesn't matter what you draw in between, but those things have to be there. That shows you the limit from the left and the limit from the right are both equal. Now the actual value of the function is different there. That's okay. Where should I take this function next? Well, this is telling me where I have to take it. The limit from the left as x approaches 8 from the left of f of x is 1. So I think I screwed up here. That should be down a little bit farther. So let's just apply a little Photoshop here. There you go. Never happened. So there you go. As x approaches 8 from the left, oh, here we go, 8 from the left, the limit is 1. Beautiful. We also have to do something likewise as x approaches 8 from the right. It's going to get down to -3. So basically you're going to have some kind of a line here that gets to -3. And then I think we've got the rest of everything. So, yay. Looking good on that one. All right. Comments on that last one there? Let's see. I think that's it for this section. So, the big message overall from this section is that when these limits exist, the fact that the limit as x approaches 0 of f of x is 4 tells you that the limit from the left and the limit from the right have to be equal. If they're not, in fact, let's end things this way. What would you say about the limit as x approaches 8 of f of x? What does that equal? Yeah, they'd be undefined or does not exist. One of the two. Either one is fine. Yeah, because the limit from the left and the limit from the right are different. So the overall limit doesn't exist. Excellent. Excellent.